So now let's talk about exponential growth. And that's often concerned with amounts of times until something occurs. You can think of the amount of a time till an earthquake is going to occur. You can think of the amount of time that for long distance calls. For me, I think about exponential distribution is say I buy a new battery and then I want to know how long that battery is going to last in my car. Because with like car batteries, the time never goes up that it's going to remain. The time always goes down. And think about car depreciation. So you buy that brand new car, you drive it off the lot, and it starts losing value, and it will always lose value. And eventually it'll kind of, you know, level off. But then again, potentially your car value could go to zero. So this is what it looks like. So it starts high and then it goes down. So think about this one. This is, we've seen now uniform distribution. We saw a little bit about normal distribution, but we're going to hit that harder after this section. But what this is so I can see the probability of 2 to 4, and I'm looking for that area in purple. And again, it starts high and it goes down. So we have something called a memory-less property. So what that means is that an exponential distribution is memory-less. That means the chance of the event occurring does not depend on previous trials. Therefore, the occurrence rate remains constant. So the memory-less property indicates that the remaining life of a component is independent of its current age. For example, random trials of coin tosses demonstrate the memory-less property. But a system that has wear and tear on it like a car is not memory-less because the way it's going to be is dependent on the time in the past. So for exponential distributions, we're going to say X is a continuous random variable since we're measuring time. So say that the mean is 4 minutes. To do any calculations, M is the decay parameter, which is the maximum value on the y-axis. And I'm going to show you a picture of that in just a minute. So M is not the mean. Remember, this right up here is mu. This is an M, and it means the decay parameter. To get M, we do M equals 1 divided by the mean. So M equals 1 over 4, or 0.25. The standard deviation in an exponential distribution is the same as the mean, so it's 4 for this problem. And the distribution notation is X approximate the exponential distribution with the decay parameter. So I just wrote it here that X approximates the exponential with 0.25. So this is what it looks like. Again, this is the highest point for this distribution on the y-axis. And you can see it's going down till it gets really, really close on the x-axis, and the mean equals 4. All right, so we do have very similar to what we had in binomial. We have PDFs and CDFs. So the probability distribution function is f of x equals ME minus MX. So let me do that to make it look nicer because I don't like the way that it did that. So we're going to go back here. All right, so f of x equals ME minus MX. The E is 2.718281. It is a number that you're going to find on graphing calculators. So let me show you. So if I bring up my graphing calculator, it's right here. For me, it's second E, and that's what it's going to look like. Your calculator that you have, you can get, I think, a $20 one that has it, so you don't have to buy this graphing calculator. I just have this because I use it for my other math classes, but that's what we're talking about when we look at it. All right, and I'm going to go back to the slide. Okay, so that's what that E is. So the curve for the one we just looked at using this formula up here is f of x equals 0.25. E, again, remember that's a constant, minus 0.25 x. So x is going to be at least 0 or higher, and you're given a value. And remember, this is an exact value because we're talking about PDF, We want exact values, like what we did with binomial. Remember, the first thing we did was PDF, which is the exact value. So let's say that I want to know the probability of 5 minutes. So I plug in 0.25 e to the negative 0.25 times 5 gives me 0.072. I put it in my calculator so you can see it. So if you see here, I'm going to do it in steps. I did the E part first, the negative 25 times 5, and I got that number. And then I multiplied it by the 0.25 to get the correct answer. Do it in steps. If you do it as one thing, you're probably going to get the wrong answer. So again, I do the E part first, and then I multiply it by the M. It just made it easier for me to solve it. Okay, so that was PDF. Let's do CDF. So the cumulative distribution function, CDF, gives the area to the left. So for exponential distributions with area to the left, the formula is 1 minus E negative mx. So you can see it here. I've written it out. So 1 minus E to the negative mx. For exponential distributions with areas to the right, the formula is P where x is greater than x equals E to the negative mx. And we're going to do some examples in the next few videos.